So we want to continue on our path to having a complete toolbox for solving quadratic equations. So we want to learn to solve quadratic equations by factoring. Now, things that we've seen so far. We've seen graphing and we've seen solving with square roots. Now, graphing was limited. It's inefficient. It's limited by the accuracy of the graph, and unless the graph is given to me, I'm probably not going to choose to go that route. Square roots. Well, square roots were only a valuable method if b was equal to 0, or if it kind of looked like it was in a vertex form-ish setup. Now, factoring. Factoring is also limited, but factoring is by far the most efficient method to solve if it's possible. Now, it's limited to equations where our solutions, our zeros, our roots, are rational, meaning no non-terminating, non-repeating decimals. We're getting fractions here, or anything that can be represented as a fraction. That includes whole numbers. Don't worry, whole numbers will still be things that we get. Now, we make use of something called the zero product property. And it's going to sound really silly when we explain it. It's going to be super common sense, but somebody got credit for naming it somewhere along the line, and good for them. The zero product property. This is the idea, in fancy math terms, that no matter what real numbers we're dealing with, if I multiply them together and I get 0, then either one or the other had to be 0. Because the only way we get 0 when we multiply is if something we multiplied was 0. So how do we make use of this? Like, why is this of any value whatsoever? Well, if we think about the way things look when they're in factored form, or close to factored form, when we finish factoring, we've got one factor times the other equal to 0 in our equation. Well, if we think about those two things as A and B, when we multiply them together and get 0, that means something has to be 0. We want to find what makes that thing 0. We want to find what makes A 0. We want to find what makes B 0. So the zero product property says that I can set them each equal to 0 to figure that out. Now, in doing that, I've created two really quick linear equations to solve, all based on that premise of something had to be 0. I add 5, I divide by 2, I get x equals 5 over 2. And in the other one, I just subtract 3 and I'm done. But those are my two solutions. Those are the two x-intercepts of what that graph would be. But you're saying to yourself, if that's intercept form and factored form were kind of the same thing, why wasn't it just 5? Well, that equation that we were just looking at wasn't quite in the factored form that we know. The factored form that we know was some quantity A times x minus p, x minus q, where we were very careful about the coefficient of x always being 1. In order for us to take that example we just had and write it with coefficients of 1 instead of that one factor that had a 2 in front, we'd have to take the 2 out. And in taking the 2 out, we'd get x minus 5 over 2 times x plus 3 equal to 0. Now if we looked at it and said, oh, p is 5 over 2 and q is negative 3, we would get those answers that we expected. But I'm willing to bet that you don't want to have to write the equation with a fraction as what's inside of the factor. We should just make use of the zero product property. Solve a simple little linear equation and be done with it. So, an example. What are the solutions to the equation 4x minus 1 times x minus 2 is equal to 0? Well, this one's already been factored. That's how you end up here. So we make use of the zero product property. When I set 4x minus 1 equal to 0 and x minus 2 equal to 0, that's what I'm doing. And then I solve the linear equations that result. So x equals 1/4 or x equals 2. What if it took a little extra work? meaning it wasn't already presented to me having been factored, but I might have to do it myself. That means that we have to remember that strategy that we had for factoring. It went a little something like this. We look for greatest common factor, we look for patterns. We hope that A is 1. If it's not 1, then we have to group. Now, as we go down the list, there's no greatest common factor. I don't see any perfect squares, which is the big tip-off to one of my patterns, so this isn't one of my patterns. Is A 1? A is absolutely 1. So now I need to run through my sequence. I need something that will multiply to be negative 12 and add up to negative 4. The numbers might jump out at you. If they don't, we make ourselves a list. 1 and 12, 2 and 6, 3 and 4. Those are all the possible combinations that'll multiply to 12. Now, since it multiplies to negative 12, I know the signs have to be opposites. And since it's negative 4, I know that it's the larger number that's going to be the negative number. So we look at our list, and 2 and 6 jump out at us. If that was x minus 6, x plus 2, those would be the factors of that trinomial. Now I finish. I need to apply my zero product property. X minus 6 equals 0, x plus 2 equals 0. Solve the linear equations, x equals 6 or x equals negative 2. X squared minus 4 is equal to 0. And you're thinking to yourself, but this looks a lot like examples from when we were solving with square roots. Can I just take a square root? Absolutely. Go for it. We'd add 4 to both sides, take a square root, remember plus or minus, and we get x equals 2 or x equals negative 2. If that's the way you want to do it, by all means, solve it that way. The only reason this is here is to show that we can solve this with factoring. If we go back to our strategy, is there a greatest common factor? No. Is this one of my patterns? Absolutely. I see x squared, that's a perfect square. I see 4, that's a perfect square. They're being subtracted. This is difference of squares. So this factors to be the product of a sum and a difference. I get x minus 2 times x plus 2 is equal to 0. It should be no-brainer by now, but I'm going to apply my zero product property and solve my simple little linear equations to come up with my results. X equals 2 or x equals negative 2. I get the same answers because neither one is better than the other. It's about what you recognize and what you choose to do. Last example. So thinking about the examples we've had, we should be pretty confident about the way this one's going to go. Is there a greatest common factor? No. Is this one of my patterns? I don't see any perfect squares, so no. Is A equal to 1? Unfortunately, no. I'm going to have to group. A is not 1. Here we go. We start by multiplying 6 times negative 5. Negative 30. So now I need to go through my sequence. What multiplies to be negative 30 and adds up to 13? Well, there's a couple of options here. We have to carefully think about the makeup of these numbers. It needs to be negative 30, so the signs have to be opposite. Opposite signs don't get me 13 with 10 and 3. Opposite signs will get me 13 if I'm working with 15 and 2. So I rewrite that middle term using those values. Plus 15x minus 2x, still all equal to 0. And then I group. I take two different pairs, and I find the greatest common factor. Greatest common factor is 3x in the first pair, negative 1 in the second pair, and lucky for me, I get the same thing in parentheses, so I can pull that out as a greatest common factor. So 2x plus 5 times 3x minus 1 is equal to 0. I apply my zero product property and solve the linear equations that I've just created. In doing so, I arrive at the results of x equals negative 5 over 2 and x equals 1/3. Those are my solutions.